This is Kevin Weiser, and this is presentation number 3 for Introduction to Astronomy. And today I will be talking about the Milky Way galaxy. The Milky Way galaxy is our galaxy. It is a spiral galaxy, or possibly a barred spiral galaxy, that is somewhat up for debate. And that is somewhat challenging to determine because that is somewhat difficult to determine because since we are within the galaxy, it's difficult for us to get a lot of measurements that give us clear understanding of the structure of the galaxy, unlike other galaxies where we can look at them basically from top down or from a distance and get a clear idea of their structure. Now, that does fortunately lead to some rather beautiful effects in our night sky. Here's a picture of Carl Sagan looking at the spiral arm of our galaxy in the night sky. This is actually a kind of a rare picture because the spiral arm is directly perpendicular to the horizon. Normally this is not the case. Normally, depending on which part of the hemisphere you're on and you know what time of year it is, usually the angle is quite a bit different and it's not so directly perpendicular. Now, a couple. Here's some time-lapse video of the Milky Way galaxy in our night sky, taken in the Midwestern plains with some very high-quality photographs that can look at night skies very nice. You can see the city here is already glowing. It looks like the sun's about to rise. That's actually light pollution from a city, and you can see the spiral arm and the different angles that it is across the night sky. As our Earth rotates, the spiral arm will go across the sky, and depending on the time of year and things like that, you'll get some different, you get some different but very beautiful views of the rotation of the spiral arm. A couple basic facts about the Milky Way. It is 100 to 200,000 light years across. That's approximately 30,000 parsecs, 30,700 give or take. It's about 1,000 light years wide, and much like the mathematical principles, the physics principles that apply to the solar system, they also apply on a larger scale to galaxies, whereas the spinning and rotating particles eventually flatten to a disk, only this is a disk on a much, much larger scale. It's got about 300 billion stars, give or take 100 billion. And again, that gives you a good idea of just how much research is left to still be done. If basically, give or take, a third of the total is how much we're estimating. That's how many extra stars we need to be able to quantify. It's difficult because a lot of those stars we can't see, and I'll talk about that a little more later. It's about 13.2 billion years old, so it's a galaxy that arrived, or that formed a couple 3 billion years after the formation of the universe, and so it's got a lot of main sequence stars. It's healthy, and it's right in the middle of its lifespan, and that'll be ending here in a few million years, and I'll also talk about that coming up here. Now, as far as size goes, it is a fairly large galaxy, but not the largest. There's a lot of globular clusters and dwarf galaxies that are much smaller than this, but there's also quite a few that are quite a bit larger. Here is how the universe works from the Science Channel, and they are comparing it, and they've got this nice little visual that I'm using, that I'm going to use to talk about. Now, here's our galaxy. Some very nice, pretty visuals here for it. And as they scroll out here, they can say this is a galaxy 100 to 220,000 light years across. Pretty big, but our nearest neighbor, Andromeda, twice the size of that, 200,000 light years across. So even larger. And then we have M87, which is an elliptical galaxy. It's the largest local galaxy of our local galaxy group, and it is. I couldn't find the exact details on that, but then it is dwarfed by IC1011, which is 6 million light years across. It's the largest galaxy ever found. It's 60,000 light years, or 60,000 times larger than the Milky Way. let's see here. So the basic structure of the galaxy is something like this. It is a a barred spiral. As all the different particles rotate, they flatten into a disk like this, and then because of the spiral density wave property, they further get constrained into these very specific spirals here, which our sun is a part of. Our sun's about 28,000 light years from the galactic core. The galactic core is believed to be a supermassive black hole, but we don't know for sure. There's still some debate up on that. The galactic core is surrounded by the galactic bulge, which goes outside of that 1,000 light year disk. Basically, whatever has enough gravity in the center to keep everything 100,000 light years across into its gravity well. Anything that's large enough to do that and powerful enough to do that, objects that are close to it have a drastically different and much stronger orbit, and these orbits go opposite of the disk here. We've got a picture here. There are the bulge stars, and they have random orientations. There's also halo stars that are considerably farther away, and they go way up and way below the disk, and they have random orientations as well. But those are pretty rare, and they're so far away and so small you just don't see them very often. The majority of them are within this disk, and that's what gives off the most light. That's what we normally see when we see other galaxies. And disk stars orbit in circles with the same orientation, but they do have a wave motion. They've got an up and down motion. That's part of that 1,000 light year width that we're talking about here. So that does give them some room to do that. So now, as I mentioned, most of the stars we see are in our local environment. And actually, I wanted to show there's a program called the Universe Sandbox here, and the Universe Sandbox is a simulator that allows you to do astrophysics simulations and situations that are very accurate and also very beautiful. I really wish I had known about this program when I had done my second or first presentations, but I didn't find out about it until about a couple weeks ago. So we're going to take a look here at the constellations within the galaxy, and basically this shows we've got the entire galaxy here, and our sun, as we see here, is in the center. And we zoom in here a little bit. Now you see from from edge of the screen to edge of the screen, we are at 11 astronomical units. We can go zoom all the way in here. Yeah, now here we're at 2.3 million kilometers from the edge of the screen to edge of the screen. So let's scroll it back out here a little bit to about 1 AU, rough give or take. So this is about the perspective you'd get from Earth. Pretty close anyway. And as you can see, all the constellations look like the constellations. We can change here. We can just have the Ptolemaic constellations, or we can have just the zodiac. Here's the band of zodiacs that go all the way around, just like that. I'm going to stick it to the common one, the Western constellations, because it's got the most variety here. Now, what I wanted to point out here was that all of these stars, they look like, just from the naked eye, they look like they're all about the same distance apart, and they look like they form these specific shapes, but that is only a trick of perception. People put a lot of metaphysical weight, magical thinking weight on these arrangements of these stars, but if you just scroll out a little bit, if we just zoom out here a little bit, so we're at we're going to there. Now we're at 2.3 light years already here. We got Alpha Centauri, which is part of Centaurus. It's already moving, and as we move out further, now we see these stars start to distort and change like that. Now, if you look, we don't have, they sort of look like they're constellations, but not really. We scroll out further, then it becomes just a tangled mess. And now we see some of these stars that are out here that are part of the constellations are at vastly different distances than the other stars. And if we scroll way out, we can see here that all of the stars in the constellations are actually just our neighbors in the solar system here, or in the galaxy. They're actually not anywhere near where they are. And then the second part to this is the other thing this program can do is it can extrapolate over time. So I'm going to start running the simulation now. It's keeping track of where all these stars are going and what direction they're going and how fast they're going. Right now, every second is 4 years. I'm going to bump that up to every second is 4,000 years, and then we'll see the the constellations start warping and drifting, and suddenly nothing looks at all like it is. Now, part of this is because, like I said, the stars are all going the same direction through the rotation, but they all have their own individual wave that's going up, up and down, and they all have their own trajectory, they're doing their own thing within the within the solar system, or within the galaxy. So if I scroll out farther here, we can see that it's running a little slow here. I don't think it likes running this many stars at once. But yeah, we can see. Yeah, here we go. All right, so here we've got the galaxy overall. And we can see the stars are rotating slowly. 4,000 years is when you're dealing with this scale. But you can see that in the galactic bulge, they're actually moving quite a bit faster. And then we have our neighbor Andromeda right over here too. So that's the second part I wanted to show, which is a simulation of Andromeda is actually predicted to collide with the Milky Way in a few million years. And this program can also model that. And so I wanted to show that. Now here we have the Milky Way, and we have astronomy. We got Milky Way at the mass of 1.0 Milky Ways. That's the standard. And then we've got Andromeda with a mass of 1.22 Milky Ways. And they are predicted to collide together. I'm going to change the graphics here so we have vivid, so we can see the blue here, and then the yellow, the white here is our sun. And as they start coming together, you can see the galactic core from Andromeda is starting to pull down on the disk, and it's starting to, and as the two galactic cores start to come together, all of the fast-moving objects in the galactic bulge suddenly get accelerated far more by the extra gravity working on them, and when they do that, boom! There is a massive outpouring of hugely accelerated stars that all reach escape velocity and all spread out all the way through everywhere. And you can see the effect on each one of on each galaxy. They all spiral, and the two massive gravities cause this beautiful blossom effect, where you can see all the different stars have formed this thing. Now this will eventually settle back down, and they'll settle back down into a disc-shaped form like we're used to. But also, these two galactic cores will start orbiting each other, and it's kind of like a binary galaxy. It's a really interesting effect. So anyway, but the effect is very beautiful. It's very haunting. It's going to happen millions and millions of years from now, and I have no idea what kind of crazy chaotic effects it would have on a galaxy to collide with another galaxy. I'm kind of glad I won't get to see it personally, but it is very interesting, and the end result is a very beautiful looking. I'm not sure exactly what to call it, but it's whatever image this creates. I find it very aesthetically pleasing, and I find it fascinating. So anyway, I hope this was interesting for you. I hope you learned a few things, and thank you very much for your time.